Okay, so last lecture I put this slide up where I said that the broad syllabus of 311 is basically three semiconductor devices: PN junctions, bipolar transistors, and MOSFETs, and if time permits, a couple of other interesting devices like LEDs and solar cells. And let me, before I delve into the subject, let me talk a little bit about in each one of them, these junctions and MOSFETs, what exactly will we be attempting to do? Okay, so as I said, one of the prime concerns is to understand when we take these semiconductor devices, their current versus voltage characteristics. Right, so these are electrical devices. All three of them are electrical. When we come to LED or a solar cell, then besides current versus voltage, we'll have to understand the interaction with light as well. Okay. Now, all right. So let's take this PN junction that you are well familiar with. Let's see what we'll attempt to do here. So PN junction, well, you're familiar by now. As the name indicates, it has a P and an N region. We understand why this particular junction rectifies. And we've also seen in earlier courses that if we take this PN junction and measure its current versus voltage characteristics, and you see here is on a log scale, y-axis is a log scale, x-axis is linear. So what you see here is a region which is a straight line which represents an exponential characteristics here. And we said that we can model at least in a part of the diode's characteristics by this particular equation here, ID equal to IS exponent VD by NVT minus 1 here. So we know that diode behaves like this. You've experimentally in the lab also measured and seen that it has an exponential characteristics. As I said, what we would like to do in this particular course now is to derive this particular equation. Okay, and see where this equation, how this equation comes about. We would like to get an expression for saturation current IS here. We would like to find out what this ideality factor N is. And also note that if we look at this particular equation, in fact, every equation that we will talk about will have a certain range of validity. Beyond, you can see here, this particular equation is breaking down here. There's a different behavior at very low voltages here. Similarly, if I had gone to higher voltages or currents, I would have found that this curve is no longer a straight line, but it starts curving here. So again, this will break down. So what we would like to understand is why is it deviating at high currents? Okay, what is the limit, for example, for this particular equation to be valid? How high can I go in terms of current and this equation still remains valid? Okay, and similarly, how low can I go and still this equation remains valid here? So we would like to discuss all these questions here. You also know that if I take, this is in the forward direction, if I take the reverse bias direction here, you know that the current is small, which we call as a reverse leakage current. And in 380 lab, we had, I had talked about that the current that you see here is not really the current that you see over here, IS. Okay, the current that you see in many PN junction diodes is often much larger than the saturation current that you see here. Okay, we would like to understand why. We would like to predict the magnitude of this particular current here. Reverse leakage is obviously very important. So we like to know how to keep reverse leakage current very low. And also, you know that any PN junction diode, if you go to a high enough voltage here, a breakdown occurs. So we like to know at what voltage does the breakdown voltage occur. Okay, what is the phenomena? And we'd like to predict that if I design a diode in a particular way with particular doping, we'd like to predict what the breakdown voltage would be. Okay. You also know that inside the PN junction, there's a depletion width. So we like to predict, we like to derive what is the extent of the depletion width here. We'll see a relationship like this here, which depends on doping and applied voltage and things like that. And we know that once there is an electric field, there's a voltage here. So we like to understand how much is this voltage, built-in voltage here. Okay, there's a relationship like this we like to derive here. So the idea is go inside the device, and many of the things that you are familiar with, for example, you know there's a depletion width. How much is the extent of depletion width, right? So we like to derive those and what does it depend on. Similarly, this is something that you've done in 380. if you take a PN junction diode and you switch it, you know that even in the reverse direction, it conducts for a short period, and which we call as the reverse recovery time here. It takes a certain amount of time for the diode to recover back its blocking state in the reverse bias case here. So, and this equation, for example, was stated when you did this experiment. We'd like to see where this equation comes from. Okay, how much is the reverse recovery time? What are the factors it depends on here? Similarly, this is a circuit model. Eventually, you would like to use a PN junction diode in circuits, and in order to use it in circuits, you require a model, which we call as a circuit model. And we have this particular model here, that there is this current I naught plus there is a junction capacitance or a depletion capacitance, and then there is another time-dependent term which comes about because of diffusion capacitance here. So we like to again derive this particular model here, where starting from some fundamental equations, we'd like to derive this particular model. We'd like to derive expressions for Cj that you see here, and similarly look at what is this diffusion capacitance, how is it dependent on current, how is it dependent on tau. All right. Okay. Not only that, so we like to understand PN junctions in more detail in terms of its IV characteristics and various important parameters. But another thing that I would like to do is, when I look at a PN junction, after all IV characteristics and everything that we do, we know that it has a set of important, I can characterize my PN junction with a set of important parameters. For example, how large a current can it conduct before it starts deviating from exponential characteristics? We would like to call this as a maximum forward current. Every device will have a limit on how much current it can handle. And if you go beyond that, what would happen is it would start deviating from its ideal characteristics or a normal characteristics, or if you go very high currents, it may even get damaged here. All right. So every device will have some current handling capability, the maximum current that it can handle here. So every PN junction diode will have that. We call this IF. Obviously, you would like a diode to handle as large a current as possible. You would like IF to be as large as possible here. Then every PN junction diode will have some reverse leakage current, IL. Well, you would like that to be as small as possible. Well, as I said, PN junction diode has a breakdown voltage. Well, as an ideal diode, you would like breakdown voltage to be as high as possible here. Every PN junction diode will have certain reverse recovery time, that when you switch it, it remains on for a certain period before it goes into a blocking state. So you would like this reverse recovery time to be as small as possible here. So these are all the desirable characteristics of a diode, at least for rectification application. Large forward current, small reverse leakage current, breakdown voltage, and tau. Often what happens is, we go through a particular subject, we derive expressions for IF, we derive expressions for IL, derive expressions for breakdown voltage and reverse recovery time, and often one stops there. But then in fact, a lot of interesting things begin after you derive, because you see that if I'm a designer, if I'm making let's say diodes, I'm a company making diodes. Obviously, I would like to make all these things very, very IF very high, IL very low, breakdown voltage very high, and tau are very, very low. I would like to do that, but I know that I can't. I can't because there are trade-offs. If as I try to increase my forward maximum forward current that my diode can handle, I would find that I'll start compromising on maybe breakdown voltage. I can't have that simultaneously. Very large current and very high breakdown voltage becomes very difficult, right? So we would like to understand why is it difficult. So once you derive IF, expressions for IF, IL, BV, and tau R, now you are in a position to explore the relationships between these. And you'll see that getting a large IF and getting a large breakdown voltage is difficult. It's possible, you can do that. But then if you get a very large IF, very large breakdown voltage, you'll find a simplified expression like this, that if you increase IF and you increase breakdown voltage, then what you'll have to do is you have to increase the cost. The diode becomes very, very costly. Okay, so we have all these relationships that you can extract. Once you have the expressions, you can extract the interrelationship between the parameters. And this will tell you now, also, for example, an expression like this tells you why, when you go and look at a manufacturer, you'll find hundreds or thousands of diodes. Why is it there? Because different diodes strike different compromises between these parameters here. In some diode, I have a current of 1 ampere, breakdown voltage of 100. Some other diode will compromise on forward current and increase the breakdown voltage. And therefore, you have a variety of semiconductor devices. Why? Because of trade-offs. You can't have all these nice things simultaneously. And therefore, depending on the interest, you can have one or two or three characteristics which are enhanced at the expense of others. And depending on how you strike the trade-offs, you get different varieties of p-n junction diodes, different varieties of bipolar transistors, and things like that. So this is where actually once you do that, once you derive all the expressions, in fact, a lot of fun begins when you start designing. When you start designing for a particular specs here. So you like to do that, but then you understand that if I take a p-n junction diode, I have to derive all the expressions for IF, IL, breakdown voltage and all that, and then start looking at relationships between them. Then the amount of time that you have to spend on p-n junction diode becomes very large. And then, then you don't have enough time for bipolar and you don't have enough time for MOSFETs here. So we would like to do that. Let's see how much we can go into all of these different aspects here. Okay. So again, where do we start? We are interested in these three at least to begin with. So all these, as you can see here, most of the time, what I'm going to discuss is these devices made on silicon here. So very briefly, I'm not going to go into the details. The silicon that we are talking about is a crystalline silicon. Okay. And its structure, some of you may have seen earlier. It has a structure which we call as a diamond-like structure here. This is a unit cell of silicon here. And if you repeat it, you get the whole crystal here. And so it's a diamond-like structure. You can see it's a two face-centered cubic lattices interpenetrating each other along the diagonal here. And so we'll not do much with this, at least in this particular course, with this structure here. What I want to emphasize, take away from here, is two things. One is that the lattice constant, this length that you see here, the length of the cube, is 5.43 angstrom. And based on that, I can calculate what is the density of silicon atoms. How many atoms per unit volume? Okay. So if I look at this particular unit cell, the volume is 5.43 10 per minus 8 cube. That's the volume of the cell here. And how many silicon atoms belong to this particular cell? Well, you have atoms at the corner, but they are shared with 8 other unit cells here. So the contribution of the corner atoms is 1. Then you have atoms in the center of the face, and there are 6 of them. And each atom sitting on the face is shared with one other. So you get 6 divided by 2, you get 3. And inside the unit cell, there are 4 others. So you get plus 4 here. And so you calculate how many atoms are there per unit volume, and you end up with this particular number. 5 times 10 to the power 22 atoms per centimeter cube. Okay, so that's the number to keep in mind. What is the density of silicon atoms? 10 to the power 22, 5 times 10 to the power 22. So that's one number. At various points, it will become of importance to compare. For example, we'll add impurities, phosphorus or boron or whatever, to make it N-type and P-type. And we often say that very small amounts of impurity result in drastic changes in the characteristics of a semiconductor here. A typical impurity that we add, typical concentration to keep in mind, is, let's say, 10 to the power 16 or 10 to the power 17. So you can see, and 10 to the power 17 impurity atoms create a huge change in the semiconductor. And so you can see if the silicon atoms are 5 times 10 per 22, and you are adding 5 times 10 to the power 16 impurity atoms. So you're basically adding a very, very small amounts in parts per million here. So the other thing is, note that, so this is a whole crystal, and we're talking about how many atoms per unit volume. But all the devices that you make it on the surface, right? And there are different surfaces that you can get depending on how if you're familiar, you can take a 100 plane, or you can take a 11 plane, and there are different planes that you can get through this particular crystal here. And if I take a 100 plane, 10 plane means basically the surface here that you see here, 100 here. So this plane here, how many atoms are there if I take a plane per unit area now? All right. So we are talking about this density is how many silicon atoms are there per unit area on a 100 plane. Okay. So now here you can see that if I take a 100 plane, one can do this calculation here. Again, the area is lattice constant times square, and then the number of atoms then turns out to be, this is not 10 to the power 24, this is 14. 6.8 times 10 to the power 14 number of atoms per centimeter square. Okay. Anyway, as I said, these are the two numbers to keep in mind. How many atoms are there per unit volume? How many atoms are there per unit surface here? Okay. Our interest, as I said, is in current flow. And before we start talking about current flow, we have to know what charges are there. All right. And this is something that you're already familiar, but we'll go into a little bit more details a little later on. The charges inside a semiconductor can be classified into three. There are electrons in my semiconductor. There are holes in my semiconductor. Electrons are negatively charged. Holes are positively charged. And of course, in almost all the semiconductors, almost all the time we add impurities. Sometimes the impurities are intentional. We add it. And nothing is 100% pure. So there are always some residual impurities here. So there are impurities inside semiconductor, and which are often charged. They can be positive charge or negative charge here. So these impurity atoms carry charges here. And of course, electrons and holes are there. So these are the charges that are there. The differences are that electrons and holes that we are talking about are mobile. So they can move around at reasonable temperatures. Of course, they move around and they can carry current. Impurity atoms at the temperatures that we are talking about are immobile. So they won't carry current. But because they carry charges, and charge creates electric field, and therefore, by their presence, they will affect the motions of electrons and holes here, because they create electric field here. Okay? So these are the charges that are there in my. The other thing, when I write N, I said number of electrons is N, number of holes is P. What I mean by N is number of carriers per centimeter cube. N refers to volume concentration, charge per unit volume, number of electrons per unit volume. Similarly, when we say P, P refers to number of holes per unit volume. And typically we'll use centimeter cube instead of the MKS units meter cube. This is more common, centimeter cube here. Okay. All right. So this is the picture that I have. A very simplified picture of a semiconductor, right? So you have all these red circles that you see are electrons. They're all distributed in a semiconductor. I have all these empty spaces that you see. These are all holes there. And along with that, I have these bigger atoms here, impurity atoms here. Okay, they could be positively charged, negatively charged. They could be neutral as well here. So this is the picture that I have, right? There are electrons, there are holes, and there are impurity atoms. Now, as I said, the only thing that is mobile is electrons and holes here. Now, what happens is, so you see this collection of electrons that you see here, and you could think of as a very simplified picture. You've all studied kinetic theory of gases, that when you have a collection of molecules and at a particular temperature, the molecules have a certain energy, they move around, right? So similarly, you could think of the semiconductor as a gas of electrons, and these electrons are moving around, right? So these electrons at a room temperature, at a non-zero temperature, they're moving around. But what is important to understand is the following. As they move around, let's take one electron here. As it moves around, it is free to move, but then what happens is it gets scattered. Now, in this case, you're not, it starts from here. You don't see anything in the neighborhood, and suddenly you find that this momentum changes here. It's going in one direction and then gets scattered in the other direction. So scattering occurs here. Well, scattering could occur the way I've shown here. Scattering could also occur through the impurity. If the impurity is charged, especially, let's say this were negatively charged impurity, an electron, it gets closer to the impurity, it gets repelled, and it changes direction here. Important point that I'm trying to emphasize is that there is scattering inside the semiconductor. Now, one source, impurity, is very easy to understand. The other source of scattering was the lattice itself is in motion. At a finite temperature, my lattice, all the atoms are not in their equilibrium position. The lattice, all the atoms are vibrating. And these vibrations, the lattice vibrations, they affect the motion of the electron, and they can cause it to scatter. Again, this is a topic of semiconductor physics. We'll go a little bit deeper later on, but we can't discuss this in too much detail. Important point to remember is that an electron, as it moves, it gets scattered. It gets scattered by the lattice. It gets scattered by the impurity atoms that are there. Okay. Now we can talk about what is and of course you understand that this is a random process. Some electron may move and may may not get scattered for a longer time. Some electron may move and get scattered very quickly, right? So we can talk about a time between a collision time or a scattering time. And this time, a number to keep in your mind is the scattering time is around 0.1 picosecond, very short. So as a mean scattering time, which means an electron moves and within a 0.1 picosecond or so is very likely to get scattered. Okay, so it's not able to survive for very long. It starts to move and then gets scattered. Okay, so that's the scattering time that you see here. You can say, you can talk about it as a collision time or a scattering lifetime. So 0.1 picosecond is that short. The other thing is, you can talk about how long a distance does an electron travel. Now we are talking in terms of distance before it gets scattered. This is in terms of time. How long does it survive before it gets scattered? The same thing I can say, how much does a distance an electron travel before it gets scattered here? So that we call as the length here, and that length is around 10 nanometers. So a typical electron would be moving around, we say, as a thermal velocity, and thermal speed or thermal velocity is around 10 to the power 7 per centimeter per second here, and you multiply it by tau, you get a number which is 10 nanometers. Okay, so it moves for, on an average, about 10 nanometers, gets scattered, and then starts moving again, and gets scattered again, and starts moving again, and gets scattered here. So that's what is happening here. These electrons are all moving around. Stars get scattered, and this is what is happening inside the semiconductor. Same thing is happening with holes here. Okay. The other thing to keep in mind is the electron that you see here. As I said, at room temperature is, you can think of this collection of electrons as a gas, electron gas, and an electron has an average energy of the order of kT. If you want to be more precise, you can write 3/2 kT, but as an order of magnitude is about kT. K is a Boltzmann constant, T is the absolute temperature. So average energy of an electron is 26 milli electron volt at room temperature at 300 degree Kelvin here. Okay. Of course, some electrons have higher energy. You know that there's a distribution of energy. Some have higher, some have lower. What we are talking about is an average energy of an electron, which is around kT, which is 26 milli electron volt. So that's the picture of a semiconductor that we have here. We have some semiconductor may have more electrons, less holes. Some have more holes, less electrons. But that's the picture that we have. We have electrons and holes. They're moving around and they're getting scattered. And so their motion is random. They go in one direction, and scattering is a totally random event. An electron goes here, it can get scattered up, down, right, left. It's totally random. Okay. So that's the picture that we have. So if I draw a line here, a cross section here, and suppose I'm interested in current, I've not applied any voltage here, I would expect on an average the same number of electrons which go from left to right as the number of electrons which go from right to left, right? On an average, there's no reason from symmetry to expect that more electrons are going right as compared to more going left here. So on an average, if I draw a line here or draw a plane, I would expect that net charge crossing this particular boundary is 0. Now, interestingly, net charge crossing this boundary, so what we are saying is average over a certain time is 0, right? Average charge crossing this particular boundary, this particular cross section is 0. But then if I make my time scale very, very short, what do you think will happen? You think always, if I look at within a picosecond, or I look at a very short time scale, you think number of charges which are crossing from left to right will always balance right to left? So if I could look at it, it may happen that more charges are crossing from left to right. Then after some time, more charges are crossing from right to left, and then again left to right. So what do I expect? If charges are crossing this, what do I have? I have a momentary current, right? If I look at that cross section. So what do I expect if I go to a smaller time scale and I draw this cross section? What do I expect here? I expect maybe some positive current here going in this direction, and then some negative current, and then positive, negative, more, less, right? Some kind of a random, this one here. If you average it out, 0. No net current. If I take a reasonably long interval of time, I have no current here. But I have all these charges flowing back and forth here. And this, now keep in mind, is a source of noise. You can see here in the inherent motion of these electrons, the random motion of electrons will give rise to noise here. There will always be noise because these charges are randomly moving around. I may have more charges going from left to right in a very short interval of time than going from right to left. On an average, of course, they will cancel, right? But otherwise, I'll have all these positive current, negative current, positive current. So all these semiconductors that you see here, when I make a statement, I'm making often these, when we talk about currents, we are talking about average current. But this average current is sitting on top of, if you go that, there's a randomness associated with it. There's an underlying random current here. All right. So they will always, this is the source of noise. Okay. So my average current is 0, but I have a noise component here. Okay. So keep that in mind. Although in this particular course, we are not going to talk much about noise, but you see in the inherent randomness here that there is noise in my system here. Okay. When we apply an electric field, what do we expect now? Earlier, as I said, on an average, electrons going from left to right or right to left are the same. No current is there. But now you can understand that if I apply an electric field, now electrons would have a preferred motion because the field now gives a direction, and more electrons you would expect will go from right to left than left to right because the field is now has provided a direction, right? It's no longer symmetric. Earlier we said when there's no field, there's no reason to expect. Now that there is a field, now I have more electrons, electrons will get accelerated opposite to the direction of the field. I'll have more going from right to left than from left to right. And therefore, I would get now an average current. Some current would start flowing and the average will no longer be 0 here. Okay, so let's look at it in a little bit more detail here. So this is the picture that we have at field equal to 0. If I take a typical electron and if I could follow it, I would see going like this, executing a random motion. Okay, this is the path, let's say. And on average doesn't move, right? And no net motion here. And we call average velocity is 0. There's no direction here. Okay, when you apply a field, again an electron is moving around, but then it acquires an average velocity. Okay, note that if this was the electron here, when you apply a field, now what you find is, again, there is a random motion here. It's always undergoing scattering, but then after a time, it doesn't end up here. There's a net motion here, which is opposite to the direction of the field here. So once you apply a field, an electron acquires a net average velocity. And this average velocity is what we're calling it as drift velocity. So note that drift velocity is not the actual velocity of an electron. Actual velocity of an electron that you see here is here, all this that is happening here, right? Drift velocity is averaged over time. If I take a large enough time, now I find, if I average the velocity, I find that an electron has an average velocity here, okay? And that because I've applied a field here. So it acquires an average velocity, and we call this as a drift velocity, okay? All right. So let's look at this drift velocity here. So we are calling this drift velocity as V. D refers to drift and N refers to electron. We're talking about drift velocity of an electron. And obviously you would expect drift velocity to depend on the electric field because that's the source of drift velocity. And you would expect also that as you increase the electric field, the drift velocity will increase, right? So you would expect a proportional graph here. So if I were to plot, it looks something like this here. You find drift velocity increases with electric field here. But then what happens is as you keep on increasing the field here, drift velocity doesn't keep on increasing. Eventually it saturates. It saturates. Now the reasons are more complex. We will see a little bit of it later on. The reasons are that scattering that we talked about, right? Scattering that we talked about, it does depend on the energy of the electron. If the when the field is small, the electron has a certain amount of energy. When the fields are large, the electron is taking energy from the electric field. The electron is becoming more energetic and the scattering changes. Okay, how the electron gets scattered, that changes here. And therefore changes begin to occur at high fields here. Okay, but let's look at this particular region here. I can see here that there's a region where my drift velocity increases linearly with the electric field here. and there's a region where it starts departing also. Okay, but at low fields, we can talk about a drift velocity which is proportional to the electric field. And the reason why the negative sign is there, because if electric field is in positive direction, electrons acquire a drift velocity which is in the opposite direction. So drift velocity is directly proportional to field for the low field region here. Okay, and the proportionality constant is what we call as mobility. Okay, so that's a very important material semiconductor parameter here, material parameter. If I apply a certain field, I will get a certain drift velocity, and the proportionality constant is the mobility here. Mobility, you can check the units of drift velocity is centimeter per second here. Electric field is volts per centimeter. So the mobility is centimeter square volt second here. For silicon, a typical mobility for electrons to keep in mind, mobility again varies a lot, can vary a lot. Typical mobility to keep in mind for silicon, let's say in a bulk silicon, is 1000, 10 to the power 3. Okay. So, well, suppose I have a field of 10 to the power 2 volts per centimeter, and I have a mobility of 10 to the power 3. So we can calculate drift velocities 10 to the power 5 centimeter per second. Okay. But again, remember, as I keep on increasing the field, it will begin to deviate. All right. One way of saying this is I can still maintain this relationship, but then I say mobility is a function of electric field. I no longer have a linear relationship, but then here I can say mu n is a function of E. So another way of saying is mobility is in general a function of field, right? And but at lower fields, it's a constant here. Okay. Now, I've been talking about electrons. The same thing happens to a hole. Okay. Now we'll talk about hole a little bit later, in more detail later on in terms of band, conduction bands and valence bands and all that. We'll talk about holes. But in semiconductors, very often what happens is, all of you know that hole is like a missing electron. It's like a vacant state, right? But don't carry that particular picture too far. That is a missing electron. For all practical purposes, for all measurements, a hole, think of hole not as a missing electron, but think of it as a real positively charged particle. All measurements. For example, if many of you may know that Hall effect. When you apply a magnetic field, then and if an electron is moving, the magnetic field deflects it, right, in a particular direction here. Now, when I do a Hall effect, I find electrons deflect in one direction, and similarly, the holes behave entirely like a positively charged particle. The holes will deflect in the other direction here. In fact, for all practical purposes, we know that underlying deep physics, yes, there is a missing electron. But for all practical purposes, think of it as a real positively charged particle with a certain mass, and so it behaves exactly like an electron, but with a positive charge. And so the equations and all that I've talked about, they hold for holes as well. For example, I can write here drift velocity of holes and plot it as a function of electric field. I'll get similar relationship, VDN equal to, and I can talk about mobility of holes. Just like I've talked about mobility of electrons, I can talk about mobility of holes. So I have electrons and I have holes. Each one of them can move around, and therefore I expect that the current in my semiconductor will have two components. In general, we'll have a component due to electrons, and we'll have a component due to holes here, Jn. So most of the time we'll be talking about current density. All that you need to do is multiply it by a certain cross-sectional area, and you'll get the actual current here. Okay, so current density, and so J, total current density in my semiconductor at any point, will be made up of two parts. One is electron Jn, and the other one is Jp, holes here. In general, if I have more electrons than holes, well, then I can approximate J as Jn. If I have more holes, then maybe I can approximate J as Jp here. All right, so that's the other thing. Current density, of course, will be measured in ampere per centimeter square. All right, so let's look at now. So we know that when we apply an electric field, the electrons acquire a net drift velocity opposite to the direction of field, and there's a net motion of electrons, and therefore I have a current, and we call that current as a drift current here. So let's quickly derive an expression for drift current here. So here is a bar of semiconductor, and let's take a cross-sectional area here, and we would like to find out so we have applied an electric field and electrons are drifting in response to the electric field, and I have a net a number of electrons crossing this cross-sectional area, and therefore I have a current, and I would like to evaluate the expression for current here. So the way we do it is, I have a certain drift velocity Vd. I could have put n here, it denotes Vd here. Let's take a small interval of time Vd into delta t here. All right, Vd into delta t. Now let's say I know the n is the number of electrons per unit volume. Okay, number of electrons per unit volume, and therefore the total number of electrons in this particular volume now will be equal to n is total number of electrons in this particular area. N is number per unit volume, so total number of electrons would be equal to n multiplied by, this is the length, drift velocity, so n into Vd into delta t multiplied by area, right? So that would be the total number of electrons in this particular region here. Now note that what happens is, in this small delta t, all these electrons that are here will cross this particular boundary. Okay, will cross this particular boundary. We are assuming, let's say, the electrons are moving in this direction from left to right, and the field is from, let's say, right to left here. So I can then calculate what is the net current density. Current density means how much charge per unit area crosses this particular boundary in the time delta t. And the charge that crosses this particular boundary will be equal to minus q, the charge of the electron. N is the total number of electrons per unit volume, multiplied by this length. Multiplied by this length, Vd into delta t. Right? So, and in time delta t, these entire electrons that you see here will go over to the other side here. And therefore, my current density charge, this is charge per unit area, and this is the time in which this particular charge crosses this particular boundary or this cross-sectional plane here. And therefore, my drift velocity, drift current then comes out to be minus q into n into Vd here. Very simple. The number of electrons per unit volume multiplied by q multiplied by the drift velocity. And we've already seen that the drift velocity is equal to mobility times electric field. Okay, so one can take this and plug it into this particular expression, and we get an expression for drift current, which is equal to k, q, n, number of electrons per unit volume, mobility multiplied by electric field. So I have an expression for drift current in my semiconductor. Okay. So anytime I apply an electric field and I know the electric field in my semiconductor, then, and I also have to know the electron density in the semiconductor, and I can multiply them together. Mu n is a constant for a semiconductor. I multiply them together and I get a drift current density. Okay. And then, as I said, whatever we are saying about electrons is also true of holes here. So drift current for a hole then turns out to be Q. P is the hole density per unit volume. Mu P is the mobility of holes, and E is the electric field here. So we have electron current here, electron drift current here, and we have hole drift current here. Okay. All right. Let's look at a different mechanism of current flow here. Diffusion occurs whenever there is a concentration gradient. Okay. This is something that we understand. Let's say I take a cross-sectional boundary here. Let's say I have more electrons on this side and less electrons on this side here. Again, remember, I have not applied any electric field now. And again, remember, all the electrons are moving around randomly. So on an average, if I have more on this side and less on this side, more electrons will cross from left to right than from right to left. Right? So I have a net motion of electrons across this particular boundary, and therefore I have a current. So that's another source of current without any application of electric field if I have a concentration gradient. If I have more electrons here, less here, this is what it shows. So if I have an electron density higher here and then it decreases, so I have a concentration gradient, I will have a current. So one doesn't need an electric field to create a current. Current can also flow if you can create a concentration gradient in electron. And the way we model this is, you can understand the flux of electrons that go from left to right will be equal to minus dn, diffusion constant, dn by dx. The flux, because note that if n is decreasing like this here, then dN by dx is negative, and negative will give rise to a positive flux from left to right. Okay, diffusion means it goes from higher concentration to lower concentration, and so this is the flux part here. And the flux part multiplied by the charge of an electron minus q gives us the current here. So that's the diffusion current density. Okay, so diffusion current density, then as you can see here, minus minus cancels, so you get q dN by dx. So it depends on the gradient here. The larger the gradient, the more the diffusion current density. Now, each one of these equations that I'm talking about, they can be derived from more fundamental principles here. Okay, but then we'll be talking about diffusion itself in several lectures, which we don't want to do. Okay, so the other thing is this diffusion constant. Remember, how is diffusion coming about? Because of all these electrons that are moving around randomly and getting scattered. How does mobility come about? Mobility is also all these electrons are randomly moving around. When you apply an electric field, they acquire a net motion. So you expect diffusion and mobility to be related together. Okay, and we'll see one derivation later on, and the relationship is called the Einstein's relationship, which says that dN divided by mu(n) is kT by q, is a constant for a particular temperature. So if you know mobility, you can multiply it by kT by q, which is 26 millivolt here, and you can get diffusion constant. Or either way, if you know diffusion constant, you can get mobility. Okay, so the two are related together. Say whatever we have said for electrons, the same thing is true for holes here, except that holes carry a positive charge here, unlike negative here, and therefore diffusion current is equal to minus q dp by dx here. While here, minus minus cancels here, so you get q dN by dx. All right. So we have now seen two sources of current. We have seen drift, and we have seen diffusion here. And the total current we know is made up of these two parts here. So J equal to Jn plus Jp, electron current density, hole current density. Electron current density is made up of two parts here: drift current, Qn mu and E, and diffusion current, dN by dx here. And similarly, the hole has a drift component here and a diffusion component here. Keep in mind, diffusion component here has a minus sign. All right. Let's now that we know a little bit about how current flows through drift and diffusion, let's apply it to a very simple case here. All right. So here is a very simple example. I have a bar of semiconductor, right? These blue ones that you see, typically in my diagrams, you'll find blue ones refer to the metal here. So I have two metals, let's say metals here. And then I have a wire here. I've connected it to ground here, and wire here, we've applied a voltage VA. A stands for applied voltage. The length of my semiconductor is L, and let's say the area is A. And in order to simplify a problem, I'm stating certain things, and I'm saying inside this particular semiconductor, there is a uniform concentration of electrons. Note that Nx equal to N0. And N0 is a constant. So everywhere, there is the same electron concentration everywhere throughout the semiconductor. And I'm also saying that Px is much, much less than N0. So hole concentration is very small. And, I'm sure you know that what we are talking about is an N-type semiconductor here. Very small hole concentration. Okay. So that's the situation here. Nx is equal to N0. Px is very, very small. And N0 is constant throughout. How do we create such a situation? That I'm not talking about. I'm giving you the electron concentration everywhere inside the device. And we know the boundary conditions. There is a zero voltage here, and there's an applied voltage VA, and we would like to know the current. Current versus voltage relationship for this very simple semiconductor device here. So I'm going to start, because I'm interested in current, so I'm going to start with this equation. J equal to Jn plus Jp. Now my P is very small, so I'm going to neglect Jp. So I'm left with Jn. So J is approximately equal to Jn. And now when I look at Jn, I see two components, drift and diffusion. Now the fact that I've said Nx equal to N0 is constant throughout tells me there's no diffusion component. So I cross that out. Diffusion component is gone, and I'm left with purely drift component here. Okay. So we start from the very first equation here. Then we keep Jn, and then we'll ignore the diffusion component, and we get J equal to Q N0 mu n E. Right? So that's the expression that we get here. Now, all of you know electric field is the derivative of potential here. So we write Q N0 mu n E is equal to minus del psi by del x. Psi is what we'll use for potential inside the device here. So we'll use the symbol psi for potential inside. Okay. So we get J equal to minus Q N0 mu n del psi by del x. All right. So we have this. Now we have to relate it to the boundary conditions here. So now what I do is, note that I take dx here, J dx, and I have psi here, and then I integrate from 0 to L here. Now several things are happening here. Let me explain. Dx I have taken here, and when I'm integrating from 0 to L, I have taken J out. Why have I taken J out? Why have I taken J out? I'm assuming something. There are two things that I'm assuming. One is I'm assuming steady state. Steady state. What does steady state mean? You will hear this phrase again and again in semiconductors. Steady state. Steady state means there is nothing that is changing with respect to time. All the time variations have died out. Okay? Which means what? Anything that you take inside my semiconductor, electron density del n by del t is 0. Z is any quantity. There's nothing which is changing with time now. All right. Steady state means that all the transients have died down. You know, if I suddenly apply a voltage here, maybe there is some transient and all that, but all the transients have died down. Nothing is changing with respect to time. Now, if nothing is changing with respect to time, why do I say that J is constant throughout the device? I'm saying J, the current is independent of position. Why? Right? Because you would expect that if I have a certain J here and a different J here, what will a different J at different places imply? More charge is entering and less is coming out, so it will imply accumulation of charge. So it would imply charges are piling up or charges are decreasing. It would imply things are changing with respect to time, which I've said is not possible. So because del Z by del T equal to 0, Z could be charge, Z could be N, P, anything, right? Because nothing is changing with respect to time, current has to be the same everywhere. Now remember, this is for total current. Total current. It need not be for Jn or Jp. We will see that later on. All that it says is the total current must be continuous. Must be the same everywhere here. That's why I've taken J out. Right? The other thing that you note here is when I'm integrating, of course, I'm assuming the problem says that N0 is constant. So we have taken it out. Mobility, we are assuming it to be a constant, as a material constant. So we have taken it out. Now we are integrating here. At this point, we have said voltage is 0. And at this point, we have said voltage is VA inside the device. We are inside the device here. So what we have assumed is what we call as ideal contacts here. That whatever voltage you apply here, that voltage has gone through the contact and has appeared inside, right here inside the semiconductor. Because this equation, remember, is an equation for the semiconductor here. So what we are assuming is sort of transparent ideal contact. Whatever you apply here, it just goes in. And the voltage at that end is VA. Yeah. Metal semiconductor junction would have. Yeah, that's what I'm saying. That's why, remember, we have said ideal contacts right now. Okay, so I'm assuming that the contacts are ideal. Whatever you apply here goes in. Whatever you apply here just goes in and appears as 0. So 0 and VA here. Many contacts come, I can make contacts which come close to this particular property. Okay, so whenever one is talking about ideal, of course, ideal will never exist. But then, as I said, I can make practical contacts which come close to this kind of a property here. Whatever voltage up. So what we are saying is, whatever voltage difference that you apply here, the same voltage difference will appear across the semiconductor. Very little drop will be there at this junction, metal semiconductor junction, and very little drop will occur at this particular junction here. So the voltage drop, the external voltage will appear inside the semiconductor also. Okay, so that's the other thing. Ideal contacts one is assuming. So we have 0 to VA. So now it's a simple integration here. So we've assumed this. J is constant. So let's integrate this here. So if you integrate, This will give you simply L here, and this will give you minus VA here. So you get J equal to Qn0 mu n VA by L here. And immediately you can see that J current is directly proportional to VA. If you want current, all that you need to do is multiply J by the area. So you get A into Qn0 mu n VA by L here. And therefore, what you see is an Ohm's law. Current is directly proportional to voltage here. So if you have this piece of semiconductor with same electrons everywhere, you apply a voltage, it will follow an Ohm's law with a certain resistance now. I equal to VA by R. All this thing can be written as R here, VA by R here. And then R we can write as rho L by A, you can see here, and we get resistivity. An expression for resistivity, which is 1 over Q mu n N0. So through this application of our equations for drift and diffusion current with appropriate boundary condition, we have shown that this particular semiconductor with uniform electron concentration everywhere acts like a resistor with a resistivity equal to 1 over Q mu n N0. Some people talk about conductivity, which is 1 over resistivity. So conductivity is Q mu n times N0 here. Okay. So that's the conductivity of this particular piece, and it acts like a pure resistor. All right. So similarly, next lecture we'll see application of these simple equations to slightly more complex problems here. Okay. So let's stop.